Okay, so T final must be V naught over, what was alpha again? Oh, all this crap. Okay, so I have to multiply that by R, so this is going to look like mu sub k g m r squared over I prime plus mu sub k g. Does that have any chance of being correct? Certainly it seems like I should factor out the mu sub k and the g. And then on the bottom, I have a 1 plus mr squared. Oh yeah, that's going to work. Mr squared over I prime. So if it's a uniform sphere, what is I prime? 2/5 mr squared. So this would be 2/5 mr squared for a uniform sphere. So that's 1 over 2/5, that's 5 halves, plus 1 is 7 halves, and the bottom is 2 sevenths. Not what I cared about yet, but at least it gives me the wherewithal to plug in to find what is the speed when it rolls without slipping. So V at T final is V naught minus mu sub k g T final. And you can see the mu sub k's and the g's go out, and we're left with V naught minus 2/7 V naught, or 5/7 V naught. Question? Light bulb? Yeah? Okay. So that was a lot of work. Are we happy that 5/7 is less than 1? Why not? Say again? He likes 5/7. Okay, yeah. I would be really surprised if the bowling alley speeds up the ball while it's also spinning it up. It does seem to me like the force of friction moving backward, is going to slow up the motion. So 5/7. This was painful. Now it's time to use a much more insightful approach. I only need this much. And that is, take advantage of the freedom that we have when we're using angular momentum and torques to pick an origin that simplifies the problem. So I want to pick an origin where I don't have any torque. Now I need to pick this one where I'm not allowed to move it around. It has to be fixed in an inertial reference frame. But any point on the floor will work just fine. Because these two forces, each one produces a torque, but the sum of those is 0. Those are always equal and opposite, and they act along the same line. And in calculating a torque, you can always translate a force parallel to itself and doesn't change the magnitude or the direction of the torque. So if I pick this point, what's the sum of the external torques? 0. So the sum of the torques, well, that's the time rate of change of the angular momentum. But this is 0. So therefore, L is a constant. So all I have to do is write down L initial is equal to L final and basically be done. So L initial Does it have any angular momentum about that origin? It's not spinning. But it's translating, it has only orbital, which is r cross r to the center of mass, cross p, it's moving that way. So r cross p into the board, and the perpendicular distance to p is just the radius. It doesn't matter how far it's moved down, it's just the radius. And so this one's not hard to evaluate. This is r times m v naught, and that's into the board by the right-hand rule. The final angular momentum will be same thing, except it's moving at a different speed. Its radius hasn't changed, its mass hasn't changed, still moving to the right, so it still has orbital angular momentum into the board, but it now has some spin angular momentum, and that also is into the board. Okay? When it rolls without slipping, there's a relationship that we already discussed between omega and v, namely that omega here is v over the radius. And so, having just perfectly run out of board, well, maybe I'll cheat and use a little bit over here. I have L final is equal to mr v plus I prime v over r in. Okay, and that's supposed to be equal to mr v naught, both in. So I'm just going to equate them, divide out m and r. So I get v naught is equal to v plus I prime. I have to divide by mr. Okay. I prime over mr squared we said was 2/5. So this is 7/5. V, that is to say, V final. Oh, I should have been subscripting final. Oops. So V final is equal to 5/7 V naught. Much easier. So if you can find a suitable reference point, you can, so that the sum of the torques vanishes, then you get to apply a conservation law. What we don't get is how long would it have taken in order for this to happen. We just immediately get how fast will it be rolling and how fast will it be moving once it does roll without slipping. Okay? Yes, Elena?
Explain why that reference point has torques 0.
Yeah. She wants to know why, how do I know that this reference point has no torque? Okay, so first consider gravity. Is there a gravitational torque about the reference point? So the direction of gravity is down. So R cross F would be, yes, there is a gravitational torque into the board. Right? And in fact, imagine that it's not moving this way and all of a sudden you dissolve the floor underneath it. What's the bowling ball going to do? It's going to go down, and that would in fact correspond to getting a rotation around into the board with respect to this reference point. So how do I know I got nothing? Well, the normal force is equal and opposite to gravity. So the normal force, R cross F, is out of the board. And furthermore, the distance, the perpendicular distance to the line of action of both those forces is the same. So those torques are equal and opposite and wipe each other out.
That makes sense. Now, what about the friction?
The friction force, the line of action passes right through that point on the floor, so the perpendicular distance is 0. So the magnitude of the torque R perpendicular times F, well, R perpendicular, 0. So it goes away. Okay? Good. Yeah?
It's not really perpendicular distance, is it though? Like, for when you're saying that the final velocity is at a radius r,
Yeah.
and at a different radius, so you just move to the right. But it's
Well,
just the difference.
so it depends on what you mean by radius. So when I've been saying radius, I mean the distance between the center of the ball and its periphery. Not any of these things that I'm writing with a vector sign and an R. Okay, a vector sign and an R to me means a position vector.
Okay, yeah.
So the position vector here of the center of mass with respect to that reference point would look like this. And as the ball moves, that's clearly changing. However, the issue for angular momentum, the orbital angular momentum, r cross t, is either that I take the perpendicular component of the momentum and multiply it by the full length r, or I take the full length r, the full length p, multiply those times what? The sine of the angle between them. So the sine of the angle between them is that angle. And as it moves to the right, that angle is getting smaller and smaller, and the sine is getting smaller and smaller, while r gets bigger, but in fact something stays constant, because that angle is the same as this angle. And so the length r times the sine of that angle is that distance, which I call r perpendicular. So that distance, r perpendicular, is not changing as the ball rolls.